Hello, my name is Nandakumar. I'm here to show you how I solved the question from level 1.4.10, which is a Newton's law of cooling question. Um, we are given that dx over dt equals negative k times x minus a, where x is the temperature, t is the time, a is the ambient temperature, and k is a proportionality constant which is greater than 0. In this specific case, we are given that A equals A naught cosine of omega t, where A naught and omega are constants. This means that the ambient temperature oscillates, sort of like night and day temperatures. Um, Part A states that we have to find the general solution, and part B shows that we have to find out whether the initial conditions make much of a difference and why this is the case. Hold on a minute while I change to my iPad. Okay, so we know that dx over dt equals minus k of x minus a. We are also given that a is equal to a naught cosine of omega t. This means that dx over dt is equal to minus k times x minus a naught cosine of omega t. Now, just by looking at this, we can tell that we can't really use separation of variables just because of the t that exists over here, or cosine of omega t that exists over here. So what we can do is make this into a linear equation and solve it using linear. So going in that case, we know that dx over dt is equals minus kx plus k a0 or a naught cosine of omega t. The minus here and here cancels to become the positive here. Now we know that a linear equation is of the form dx dt plus kx equals this. So we can move the kx to the left to write it as dx over dt plus kx equals a naught cosine of omega t. So we know that a linear differential equation is in the form of dy over dx plus constant times y is equal to another term which does not have a y. In this case, the y is x and x is t. Um, Hence, this is in the form of a linear differential equation of dx over dt plus kx equals a naught of cosine of omega t, which does not have an x term. We can solve the differential equation by finding p of t. The p of t term is the term that is multiplied to x, which is k. So p of t equals k, and mu of t equals e to the integral of p of t dt, which equals e to the integral of k dt, which further equals e to the kt. Multiplying the mu of t terms to this equation, we have e to the kt dx dt plus k e to the kt x equals, oh, I apologize, I just realized that I had not multiplied the k in over here, so this is k a naught cosine of omega t. So this equation further equals k, sorry, k e to the kt a naught cosine of omega t. Now we multiplied nu of t into the previous equation to make it easy to find the antiderivative of this term. Sort of like a reverse of the product rule. So the reverse of the product rule in this case would have been e to the kt times x, or else the d by dt of it. Now let's verify this just to make sure that we're not making a mistake, or at least I'm not making a mistake. So applying the product rule over here, we have x times k e to the kt plus e to the kt times dx over dt, which is what we have over here. So that's good. We can remove this and go on with the rest of our problem, knowing that we did not make a mistake over there. Cool. So this equals k e to the kt a naught cosine of omega t. So we integrated on both sides with respect to dt. The dt here and here cancel, so that this becomes x e to the kt equals k a naught integral e to the kt, sorry, cosine of omega t dt. I've taken the k and a naught out over here because they're constants. It is not easy to find the integral of this term because we have to use the integration by parts to find that. So I'm going to do that on the side over here. Let's put I equals integral of e to the kt cosine of omega t dt. Okay, that's easy to write. Cool. See, let u equals cosine of omega t and dv equals e to the kt dt. We have du equals minus sine of omega t dt over omega, and we have v equals 1 over k e to the kt, as integral of u dv equals uv minus integral v du. We have e to the kt over k cosine of omega t plus integral e to the kt over k, oops, k times omega sine of omega t dt. In the interest of time, I'll have to solve this integration by parts by myself, just because there's not much time left. So I'll talk to you after I've solved this. Let me show you what I've done so far. But before that, let me explain something. Over here, I had a positive instead of a negative um, here. This is because the negative over here and the negative from here cancels each other out. So the next step from here would have been I equals like this, which is basically what I have written over here. And further using integration by parts, I have I equals e to the kt over k cosine of omega t plus, omega over k times e to the kt over k sine of omega t minus omega over ki. And this is the rest of my solution, where I, I basically multiply the omega over k in and then bring the I to the left side, which I have over here, k squared plus omega squared over k squared. This was originally 1 plus omega squared over k squared, which I wrote it in this form. Then I have the k squared and k squared cancelled from both these sides, which then caused me to bring the k squared plus omega squared down over here to get this equation. I equals e to the kt times k omega t plus omega sine t the whole over k squared plus omega squared. Now, coming back to our original equation, we had x e to the kt equals k a naught I. That is x e to the kt equals k a naught e to the kt times k cosine of omega t plus omega sine, let me get this out of the way, of omega t the whole over k squared plus omega squared plus c, because of the constant of integration. We can bring the e to the kt over here. That will give us x is equal to k a naught k cosine of omega t plus omega sine of omega t over k squared plus omega squared plus c e to the minus kt. This will be our general solution. So this is our answer for part A. Now, as time goes on, or when t goes to infinity, we know that this goes to 0. This goes to 0, and cosine and sine oscillate, so that does not affect our general solution. Therefore, in the long term, we know that the initial conditions will not make much of a difference. So that will be our answer to part B. Now, time's almost up, so I'll post another short video showing the applet visualization and how I went about to do that. Thank you for watching this video, and I hope you watch my next video as well.